Hey everyone, welcome to this explainer. Today, we're diving into the hidden, three-dimensional world of stereochemistry. If you've ever looked at a chemical structure drawn on a flat piece of paper and thought that was the whole story, well, you are in for a major surprise today. We're going to explore how the exact same atoms, connected in the exact same order, can create entirely different molecules just by taking up different spaces in 3 dimensions. Think about this for a second. How is it that one molecule can cure a nasty bacterial infection while its exact identical twin, literally made of the very same carbon, hydrogen, and oxygen atoms, does absolutely nothing at all? Or, crazy enough, how can one twin be a perfectly safe painkiller and the other just be completely inactive? That right there is the secret of stereochemistry, and we're going to decode exactly how that happens. To figure this out, we've got a great roadmap today. We'll start with the mirror image mystery, decode optical activity, visualize some 3D molecules, go beyond the asymmetric carbon, look at stereospecific chemical reactions, and finally, talk about why stereochemistry matters. All right, part 1, the mirror image mystery. So, let's lay down the basics. We need to talk about the different flavors of something called stereoisomers. First up, enantiomers. Just think of your own hands. Your left and right hands are mirror images of each other, right? But try stacking them perfectly on top of each other with the palms facing the same way. Doesn't work. They are what we call non-superimposable mirror images. Next, we have diastereomers. These are stereoisomers that just straight up aren't mirror images of each other at all. And finally, the mesoform. This one's pretty cool. It has asymmetrical parts, sure, but the molecule as a whole is perfectly symmetrical right down the middle, which actually cancels out its own optical superpowers. Take a look at this. Notice how D-glyceraldehyde has that OH, the hydroxyl group, attached to the central carbon and pointing off to the right side? Now check out its mirror image, L-glyceraldehyde. It has that exact same OH group, but pointing to the left. If you literally tried to slide that L form right over the D form, the atoms just wouldn't line up. This simple idea of handedness is basically the root of this entire concept. Moving on to part 2, decoding optical activity. So now we know what these chemical twins are, but how do we actually tell them apart in the real world? Because let me tell you, if you had a beaker of the D form and a beaker of the L form, they would look completely identical to the naked eye. In fact, enantiomers share the exact same melting point, boiling point, and density. They are true chemical twins. But here's the catch. They reveal their true identities in 2 highly specific ways. First, if you shine plain polarized light through them, one twin will twist that light to the right and the other twist it to the left. Second, the way they react with other chiral molecules, like the biological enzymes inside your body, can happen at completely different speeds or sometimes not at all. Things get a bit more complex when a molecule has multiple chiral centers, meaning multiple carbons, hooked up to 4 different groups. Take 2,3-dibromobutanoic acid here. We use these terms erythro and thrio. Basically, if you draw the molecule out and the identical groups, like the bromines here, are on the same side of the projection, boom, that's an erythroisomer. If those groups are on opposite sides, that's a threoisomer. It's just a super handy shortcut for quickly describing these complex 3D relationships. All right, section 3, visualizing 3D molecules. Okay, so since we can't all carry around 3D plastic model kits everywhere we go, we need a way to translate reality onto a flat piece of paper. On the left, you've got the wedge dash formula. Those solid, thick wedges, think of those as bonds popping right out of the page towards you, and the dashed lines are receding back away from you. The absolute brilliance of the Fisher projection formula on the right is that it flattens this whole thing out. That crosshair shape basically tells you anything on the horizontal line is coming out for a hug, and anything on the vertical line is pointing away. But here's the thing. To keep that 3D information accurate, we have to play by some incredibly strict rules when manipulating these 2D drawings. The source material dramatically calls these forbidden turnovers. You absolutely cannot pick a Fisher projection up off the plane of the paper and flip it over like a pancake. If you do that, you accidentally create the enantiomer, the mirror image. You're totally safe to rotate it 180 degrees around on the paper, but rotate it just 90 degrees? Nope, forbidden. That ruins the entire spatial configuration. Okay, section 4, beyond the asymmetric carbon. Up to this point, we've basically relied on having a central carbon atom bonded to 4 different things. But hey, nature loves breaking the rules. Let's look at molecules that pull off chirality without a traditional asymmetric carbon at all. Take a look at this class of molecules called allenes. They have 2 double bonds right next to each other. And because of how their p orbitals overlap, those double bonds are actually forced to sit perpendicular to one another. What does that mean? It means the groups on the far ends of the molecule are stuck in different planes. So even without an asymmetric carbon, if you have different groups on those ends, the whole molecule is asymmetric. You get non-superimposable mirror images. We see something similar with these bulky biphenyl compounds. Now, normally, a single bond acts like a spinning wheel on an axle. Nice free rotation. But if you cram large, bulky groups right next to that central single bond, they literally bump into each other. They create a microscopic traffic jam. This stops the rotation dead in its tracks and locks the two phenyl rings at an angle. We call this Isomerism. The molecule becomes stuck in a rigid chiral shape purely because it's too crowded to spin.
Moving right along to Section 5, Stereospecific Chemical Reactions. Because these 3D shapes completely control how molecules collide in the lab, let's see what happens when we try to add bromine to a double bond in but-2-ene. Bromine atoms like to add from opposite sides. We call it anti-addition. So the 3D shape of whatever we start with totally dictates our final product. If we start with the Z isomer, where the methyl groups are on the same side, we get a racemic mixture, which is essentially a 50-50 mix of two enantiomers. But run that exact same reaction on the E isomer, where the methyl groups are on opposite sides, totally different result. You get a single optically inactive mesocompound. The shape you start with literally locks in your final destination.
And that is exactly why we need to distinguish between two really important terms here. A stereospecific reaction, like what we just saw, is a hard guarantee. Starting with isomer A guarantees product X, and starting with isomer B guarantees product Y. A stereoselective reaction, on the other hand, is more like a really strong preference. The reaction could technically make multiple isomers, but because of the 3D crowding, one specific stereoisomer just predominates over the others. It heavily favors one path. And finally, Section 6, why stereochemistry matters.
So let's bring this all back down to Earth. Why does any of this microscopic 3D stuff actually matter to you and me? Well, it's because the human body is an incredibly chiral environment. Our enzymes, our proteins, our DNA, they all have a specific handedness. So our biology literally reacts to these enantiomer twins as if they are completely different substances. Minus penicillin, that's a life-saving antibiotic. Its plus enantiomer twin, totally useless. Minus nicotine is highly toxic, but its twin is much less so. When you grab some ibuprofen for a headache, only the S enantiomer is actually relieving your pain. And my favorite example, we burn D-glucose for energy all day long, but if you were to eat L-glucose, your body would have absolutely no clue what to do with it, and you'd just excrete it right out. As the source material puts it so perfectly, this handedness isn't just some obscure quirk of lab chemistry. It is a fundamental design principle of life, of medicine, and literally the universe itself. Without stereochemistry, modern pharmacology as we know it simply wouldn't exist. We literally have to design drugs to perfectly fit the microscopic chiral locks inside our bodies. It really leaves you wondering, doesn't it? If just flipping a single, invisible atomic group can mean the difference between a miracle drug and a useless powder, what other microscopic, invisible differences are out there, quietly dictating the reality we experience every single day? So next time you look at a simple chemical formula, remember to ask yourself, what is it hiding in the third dimension? Thanks for hanging out with me for this explainer, and keep questioning the invisible.